Hello, class. So in this video, we're gonna finally talk about this example that I was talking about earlier about modeling population growth. Specifically, in this case, it's going to be bacterial growth, but I'll tell you what are the assumptions that you need for your population in order for this to work. Okay. Now, another thing we're going to need for this is how to find the general solution of an expression of this form, dy dx equals by plus c, but we already saw how to do that in the previous video. We went over all this work here. So you can go back and review that. And we're going to do it here again, just for another example. So assuming a rich environment, that means that there's enough space and enough resources. Well, a population is growing, so the only way we can assume it's growing is if there's enough space for it to grow and enough resources to sustain that growth. Okay? So assuming one, a rich environment, and second, and this is important, that the bacteria don't die. Okay? So we're going to be working with a bacteria colony. So under these two assumptions, you have a rich environment and that there's no deaths in your population, then we can work with this model. Okay. So what's the model going to be? Well, we're going to have to come up with it. And the model is going to come from a differential equation. We're going to write a differential equation that models this population growth. Okay. Now, given these two assumptions, rich environment and bacterial growth, what you can conclude, and I'm not going to prove this, is something you can read it up online if you want, but given these two assumptions, you can assume that the rate of change of the bacteria population is proportional to the current amount of population. Now, these are both things that we talked about before, right? So we look at rate of change. Remember, for you, that means derivative. Right? Rate of change means derivative. They're interchangeable. And we also have proportionality to the current population. Remember that two quantities are proportional if they are scalar multiples of each other, if one is a constant times the other. So what does it mean that the rate of change is proportional to the population? How can we write that mathematically? Well, the population is given by P of t. Since it's clear from the problem what the independent variable is, in this case t, I'm not going to write P of t, I'm just going to write P. So P is population. Now, the two quantities that are proportional are the population and the rate of change of the population. Again, rate of change is derivative. So what's the rate of change of the population? We can write that as dp dt. How do I know that it's the rate of change with respect to t? Because t is the variable that is changing. The population is changing as time is changing. So t is the independent variable, so we're going to take the derivative with respect to t. We're interested in the rate of change with respect to time. And then finally, the last thing we need is the fact that, as I said, two quantities are proportional if one is a multiple of the other, a constant multiple. So we can write dp dt equals a constant k times p. And that is precisely how you write proportionality mathematically. And now this is something that models the growth of the bacteria population, because here we have an expression for the growth of the growth or the rate of change of the population. You can think of it as a growth rate if it's increasing, or decay rate if it's decreasing. So this is our model that gives us the growth of the bacteria colony or the bacteria population. Now, again, you have to be able to identify that if we're looking for solutions of this differential equation, solutions are going to be functions p that you can plug in, and they satisfy the equation, get equality. That means the solutions for this are population functions. So in fact, we can model the population. If we're able to solve this differential equation, we can model the population of this bacteria colony at a given time t. And I think I'm giving that t as so t is time in days, t greater than or equal to 0. Okay. So that's basically how you come up with the differential equation to model this system. Just use the assumptions. The rate of change is proportional to the current population, and that's basically how you set it up. Now let's actually try to solve or find the general solution to this differential equation. That's another thing I want to mention. When I say solve, think of it as being interchangeable with find the general solution. Let's find the general solution. Again, I'm going to interchange it with solve, the differential equation. So how do we find the general solution? Again, we can't just integrate both sides, right? Because we don't know how to integrate the function that we're looking for. So we have to do something else. But that something else comes when you realize that this has the same form as this differential equation, a constant times the function plus a constant. It has the same form. It's just that the extra constant is 0. But it has the same form. dp dt equals a constant times the function plus a constant. So what do you do then? What's the method? You first divide both sides by this, by the right-hand side. Okay, so we have that dp dt divided by kp equals 1. And then again, we're assuming that kp is not equal to 0. Integrate both sides with respect to t. And now here, you can skip, from now on, you can skip these steps if you want. So I'm going to write all the steps, and I'm going to tell you which one you can skip to. So here we take the integral with respect to t of both sides. And then again, by the formula I gave you for differentials, we know that dp dt times dt is just dp. And again, the way to remember that is think of canceling the dt on the bottom with the dt on the top. Again, it's not really that we're canceling, we're using differentials, as I explained in the previous video. But for now, if you want to remember, just think of it as cancel it. So this becomes dp over kp equals the integral of 1 dt. So now, in your work, in your homework and in exams, if you want, you can skip from, no, actually not from this step. You can skip from this step directly to this step, meaning that you don't have to show me this step here where we are canceling the dt's. That's fine. Or, okay, not canceling, but rewriting the expression. You don't have to show me that. If you want, you can. In fact, I always write it like this, just so I don't forget how to do it. But if you want, you can go directly from this expression to this expression. Okay, now we integrate both sides. So the right-hand side, again, is easy. The integral of 1 with respect to t, is just t plus some constant. Let's call it c. And now we also have to integrate the left-hand side. So let me do the work here. And again, for something like this, for our purposes, p, even though it's a dependent variable, for the purposes of integration, it becomes the independent variable. So integrate this as you would in Calc 2. So as before, well, you can do a few things. If you want, you can move the 1 over k outside. Now you need a u substitution. Oh, I guess you don't need a u substitution now, because we know that an antiderivative of 1 over p is the natural log of the absolute value of p. Right? And then we have this constant of integration, let's say d. So in practice, what I actually did is I multiplied, so let me just do the step. There was another constant here, but when I multiply 1 over k times an arbitrary constant again, an arbitrary constant times any other constant, the product becomes arbitrary. So I'm just calling that product d. Okay, now that we know what that integral is, we can go ahead and plug it in to our differential, to our equation here. So its left-hand side becomes 1 over k. natural log of the absolute value of p plus some constant, let's call it d. Again, we can combine the arbitrary constants d and c to a single constant c. Now, I'm going to multiply both sides by k because the goal is to solve for p. We're going to get p by itself. So this is just algebra. Multiply both sides by k. Now, k times c, again, c is arbitrary. So an arbitrary constant times k is still going to be an arbitrary constant. Take the exponential of both sides to get rid of the natural log. Do plus or minus of both sides to get rid of the absolute value. So, sorry, plus or minus of the right-hand side. That gets rid of the absolute value. And again, this for me is a good enough solution. This is the general solution by definition. Any function that satisfies this differential equation has this form. Again, if you want, you can do the trick they do in the book where they combine, well, they write this as e to the kt times e to the c, right? So they use the product of exponents. And then they combine the plus or minus constant, they combine it with the e to the c constant. Again, e to the c is arbitrary, times the constant plus or minus, it's arbitrary. So they write all of this as just an arbitrary constant c. Again, it's the same thing, it just simplifies how the function looks. But again, I'm fine if you leave this as your final answer. But if we simplify, we get plus or minus, that cancels out with the c as well as e to the c, so it just becomes c e to the kt. Okay. And now this is the general solution, or any function that satisfies this differential equation has this form. So a nice solution form for an equation that, I mean, I guess dp dt equals kp in terms of what we're going to be doing, it's a simple one, but it's still nice that we get a nice form for it, for the general solution. Now I'm going to end the video here. We're going to do one example working with this model, and then we're going to keep going.